Dear students, good morning. Again, I welcome you all in this online class. In a series of lectures, we have discussed already the development of nuclear physics and properties of nuclei, and in continuation, today I am going to discuss the important topic which is about the force between nucleons. We have already discussed in this regard the deuteron in our previous online class, and today, in order to find the nature of forces between nucleons, we are going to discuss the neutron-proton scattering at low energies. Information on the internucleon forces can be obtained from a study of the scattering of free neutrons by protons. Two kinds of reactions can be involved in neutron-proton interaction. Out of these two kinds of reactions, one is scattering and other radiative capture. The latter has low probability. In practice, protons are bound in nucleus. The chemical binding energy of the proton in a molecule is about 0.1 electron volt. Thus, for neutron energies greater than 1 electron volt, the proton can be assumed as free. If the neutron energy is less than 10 MeV, only the S wave overlaps with the nuclear potential and is scattered. In the center of mass system, the Schrödinger equation for the two-body neutron-proton system problem can be written as Laplacian psi plus capital M upon h square E minus V or psi equals to 0, where M equals to proton or neutron mass, which is twice the reduced mass of the system. E is the incident kinetic energy in center of mass system, which is equals to half of incident kinetic energy in lab coordinate system, and VR is the internucleon potential energy. At large distances from the center of scattering, the solution of this equation is expected to be of the form psi equals to e raised power I k z plus e raised power I k r upon r multiplied by f theta, where the term e raised power I k z represents a plane wave describing an incident beam of particles moving in the z direction towards the origin or the scatter. The second term represents the scattered wave. The complex quantity f theta is the scattering amplitude in the direction theta and is to be evaluated in terms of k. The differential cross section can be written as d sigma equals to f theta magnitude square d omega, where f theta magnitude square is f theta into f star theta, where f star theta is the complex conjugate of f theta. So this differential scattering cross section d sigma can be written as magnitude f theta square d omega, where d omega is the solid angle in which particles are scattered, so that the total scattering cross section can be written as sigma equals to integration f theta magnitude whole square d omega, which is equals to twice pi integration magnitude f theta whole square sin theta d theta, because d omega, that is the solid angle, is equals to 2 pi sin theta d theta. Now first we consider the wave equation 1 in the absence of a scattering center, that is if the potential between these two particles, neutron and proton, is 0. So in that case, this Schrodinger equation becomes Laplacian psi plus me upon h cross square psi equals to 0, and the solution of this equation is psi equals to e raised power I k z, where k equals to under root capital M e upon h cross square. Now Lord Rayleigh proposed that this type of wave function can be expanded into a series in terms of spherical harmonic functions. Thus equation 5, that is psi equals to e raised power I k z, can be written as an infinite series epsilon equals to e raised power I k z equals to e raised power I k r cos theta, that is equals to summation L equals to 0 to infinity capital R L R into y L0 theta, where k equals to 1 upon lambda cross, where L is the integer representing the number of the partial waves. It as usual signifies the orbital angular momentum of the system. The radial function RLR are solutions of the radial part of equation 4, which is 1 upon small r square d by dr small r square d by dr of capital R plus k square minus LL plus 1 upon r square into capital R equals to 0. This equation has two solutions. One is not finite at the origin and cannot represent the plane wave, and the other is finite at the origin and can be represented in terms of spherical Bessel's functions as capital R L R equals to I raised power L under root 4 pi 2L plus 1 JL KR. The spherical harmonic function YL0 theta equals to under root twice L plus 1 upon under root 4 pi into PL cos theta, where PL cos theta is the Legendre polynomial of order R. For incident neutrons, kinetic energy less than 10 MeV, only L equals to 0, that is S wave involved in scattering. Then the scattering is spherical symmetric. In center of mass system, equation 6 can be written as psi equals to R0R capital Y 00 theta plus summation L equals to 1 to infinity capital RLR into Y capital Y L0 theta equals to sin KR upon KR plus in the bracket e raised to power I k z minus sin KR upon KR. Here the first term corresponds to the spherically symmetric partial wave, that is S wave. For S wave scattering, only first term is effective and therefore be written as psi S. In the presence of the scattering potential VR, we can write it as psi S equals to UR upon R. Outside the scattering potential range, the amplitude of the outgoing wave is unchanged. The change is only in phase of the wave. Thus, as R tends to infinity, the solution UR assumes the form C sin kr plus delta 0, where C is the constant and delta 0 is the phase angle. Thus, outside the scattering potential, complete wave function can be written as psi equals to C sin kr plus delta 0 upon r plus inside bracket e raised to power I kz minus sin kr upon kr, which can be again written as psi equals to e raised to power I k z plus c upon r, e raised to power I kr, e raised to power iota delta 0 minus e raised to power minus iota kr, e raised to power iota delta 0 upon twice iota minus 1 upon kr, e raised to power I kr minus e raised to power minus I kr upon twice iota. And this equation can be written as psi equals to e raised to power I kz plus e raised to power I kr upon r is common, and in bracket we find c into e raised to power iota delta 0 minus 1 upon k upon twice iota minus e raised to power minus I kr upon r into c minus iota delta 0 minus 1 upon k twice I. And this scattered wave must contain no incoming wave, and here the third term e raised to power minus I kr upon r into c e raised to power minus iota delta 0 minus 1 upon k twice iota, it represents the incoming wave, and because this scattered wave must contain no incoming wave, and therefore coefficient of e raised to power minus I kr should be 0. And by doing this we get c e raised to power minus iota delta 0 minus 1 upon k equals to 0. Therefore we get c equals to 1 upon k e raised to power iota delta 0, and by substituting this value in above equation we get psi equals to e raised to power I kz plus e raised to power I kr upon r, e raised to power twice iota delta 0 minus 1 upon twice I k. Now if we compare this with the standard solution 2, we get f theta equals to e raised power twice I delta 0 minus 1 upon twice I k, and by taking e raised to power iota delta 0 upon k as common, in bracket we get find e raised to power iota delta 0 minus e raised to power minus iota delta 0 upon twice iota, and this bracketed quantity is the value of sin delta 0. So the total elastic scattering cross section is sigma 0 equals to twice pi integration from 0 to pi sin square delta 0 upon k square sin theta d theta. Now sigma 0 equals to 4 pi upon k square sin square delta 0, and this can be written as because 1 upon k equals to 1 upon lambda cross, so it is sigma 0 equals to 4 pi lambda cross square sin square delta 0. For higher angular momentum waves, the total cross section can be written as a sum of partial cross sections, one for each L value. So the partial cross sections become sigma L equals to 4 pi lambda cross square twice L plus 1 sin square delta L. And now we come to the part scattering length. For low energy neutrons scattered by protons, k is very small, and from equation 10 we see that as k tends to 0, delta 0 again tends to 0. Thus for low energy neutrons, f theta can be written as f0 equals to limit delta 0 tends to 0 e raised to power iota delta 0 sin delta 0 upon k, which is equals to delta 0 upon k, and this can be written as minus a, and hence ur again can be written as c kr plus delta 0 equals to cr k minus A. The positive quantity A is called scattering length, and equation 13 is the equation of a straight line intersecting the r-axis at r equals to A, and is obtained by extrapolating the radial wave function ur from the point just beyond the range of the nuclear force. From 11 and 12, the zero energy scattering cross section sigma 0 comes out to be 4 pi a square, and here are the two diagrams, one for positive scattering length and another for negative scattering length. This is the extrapolation of ur, and showing the positive scattering length, and here this diagram is for negative scattering length. This is identical with the cross section of an impenetrable sphere of radius a in the limit of zero energy. The measurement of sigma 0 determines the magnitude of the scattering length a, but not its sign. Now I come to the next part, that is phase shift. So delta, as we have already discussed, delta 0 represents the phase shift. So delta 0 can be determined by solving the Schrodinger equation in the region where the interaction between the two particles takes place, making assumption of a square well for the nuclear potential. Inside the potential well of depth V0 and radius b, radial wave equation is d2u upon dr square plus capital M upon h cross square E plus V0 into ur barabar 0, where E is the energy of the particle. Now the solution of this Schrodinger equation inside and outside the well can be given as ur equals to a sin k1r, and ur outside the well, the solution ur equals to b sin kr plus delta 0, and at the boundaries r equals to b, the two solutions and their derivatives with respect to r must be continuous. So we get a sin k1b equals to b sin kb plus delta 0, and if we make equal the derivatives, we get k1a into cos k1b equals to bk cos kb plus delta 0, and by solving these two equations, this gives k1 cot k1b equals to k cot kb plus delta 0, and this relationship is analogous in the form to equation k cot b equals to minus alpha, which we have already studied by studying the problem of deuteron, where we have get this relation k cot kb equals to minus alpha, which describes the binding energy B of the deuteron in terms of the same rectangular well, where k equals to root m v0 minus b upon h cross square, and alpha equals to root mb upon h cross square. For low energy neutrons, that is, if E is very much less than V0, we may assume k equals to k1, and hence the wave function ur inside the well is nearly the same for the deuteron and the NP scattering system. Thus, for approximation, we write root me upon h cross square quote root me upon h cross square b plus delta 0 equals to minus root mb upon h square. As scattering length a is very much large than range b, thus for very low energy neutrons, kb may be neglected in comparison to delta 0, and we will get cot delta 0 equals to minus root b upon A by solving the above equation, and we get sin delta 0 equals to E upon E plus B. So by substituting this value of sin square delta 0 in equation 11, we obtain the approximate value of total scattering cross section as sigma equals to 4 pi h cross square E upon E plus B. So that's all in today's online class. Thank you.